All right, hey guys, welcome to the first module. I'm just gonna go ahead and go over the slides. If you prefer to have somebody talking about them to you guys, if you prefer to just go through them on your own, they're also available on Canvas by themselves. But here we go. We're starting with kinematics for our unit 1. And we're going to get started with what are vectors and scalars. So a vector is a quantity that describes a magnitude and a direction, and you denote vectors by putting an arrow on top of the letter associated with the value. So for example, velocity is a vector. V is equal to 3 meters per second, and you can say to the right. For a scalar is a magnitude with no direction. And so it's just going to be the letter by itself. And an example of that is speed, which is 3 meters per second in this example. So for the direction of vectors, we can think of them on a graph, and we can put them on a coordinate plane. It's easiest to just put our vectors starting at the origin. We can put them anywhere as long as they are the same length and direction. No matter where they are on the coordinate plane, they're going to be the same vector. So we have upwards is positive y. This is also written as j hat. I wasn't able to put the little hat on the slides, but just know that this is a vector, and so it has a little arrow, but for the direction vectors, we just do a little caret on top, so it's like a hat. And downwards is going to be negative y or negative j hat. Left is negative x or I hat, and right is positive x or I hat. If you're going into the page or out of the page, you can have a third dimension, which is z, which is also known as k hat, but we're just going to deal with 2 dimensions for this course. So this means when writing out vectors, you don't need to write the direction. You can just use a positive or negative. So going back to this slide, if we were to say velocity equals 3 meters per second to the right, since it's to the right, we could just say 3 meters per second I hat, or 3 meters per second in the positive x direction. It means the same thing. Okay, so thinking about these vectors, how to name them, we have them on our coordinate plane here, and they're all starting at the origin. We have vector A is equal to 2 I hat, so 1, 2 in the x direction, plus 4 j hat, 1, 2, 3, 4 upwards. For B, we have positive 3 I hat plus j hat, and C is negative 2 I hat minus j hat. You can also combine vectors. So this is called vector addition, and also there's vector subtraction, but you would just multiply by a negative, and I'll talk more about that later. So there are multiple ways to add vectors, and the following slides show them on our vectors A, B, and C that we have right here. I have a little color code for you. Yellow vectors are the original vectors. Blue vectors are vectors that I have moved, and purple vectors are the resultant vector. And the resultant vector just means the vector that is the result of the vector addition. So pretty straightforward. Okay, graphically, this is the first way we can add vectors. So if we were to add A plus B, you would move vector B so that the tip of vector A's arrow is touching the end of B. So as you can see, B just slid up over here to vector A. The tail of B is touching the tip of A. Then you're going to draw the resultant vector from the tail of A to the tip of V. And then you can name your vector. I'm choosing to name it vector D because I have A, B, and C, and then just D. And this is going to be 5 I hat because it's 5 units in the positive x direction plus 5 j hat because it's 5 units in the positive j direction. So now if we were to do A plus C, going to move vector C so that the tip of vector A's arrow is touching the end of vector C. This is tip to tail. Draw the resultant vector from the tail of A to the tip to C. Name our vector and write its vector equation. So this is going to be positive 3j hat. There's no I component, so you can just leave that out. Algebraically, so you just add them component-wise and name the vector. So this one is a little bit easier to me, at least, because I'm more of a symbolic person than a visual person. So this just helps me think of it. So here we have vector A is 2 I hat plus 4 j hat. Vector B is 3 I hat plus j hat. That's going to be 5 I hat plus 5 j hat. as you can tell, it's the same exact thing as graphically adding them. Now a plus c is the same exact thing, and as you can see, vector d is the same exact vector as we got when we did it graphically. So some examples of vector and scalar quantities. I'm going to start with scalar. Speed is a scalar. It describes how fast an object moves, and distance describes how far something is. Velocity is a measure of speed in a certain direction, and acceleration is a measure of the rate an object's velocity changes. And don't worry, I'm going to go into more details of these terms on the following slides. And displacement is a measure of how far and in what direction an object travels. So, distance, how far an object travels. Position is represented by the letter x, and distance is measured in meters. So, distance describes the total change in an object's position. Displacement is a little bit different than distance, and that can be kind of confusing at first, but I'm going to give you guys lots of practice for this. So displacement is how far and in what direction an object travels. So how to calculate displacement is going to be delta x. Remember, delta x is displacement, and position, x is position. So delta x, a change in x, is our displacement, a change in position, equals x final minus x initial. The units for displacement are meters. Okay, velocity. Velocity is speed and direction. Remember, it's a vector. So how to calculate velocity is going to be delta x, or displacement, and over delta t, which is time. And the units for this are going to be meters per second. So acceleration is a change in velocity. So very similarly, we have acceleration is equal to a change in velocity over a change in time. And the units for this are meters per second squared. Okay, so to find the distance versus displacement, the following slides show the path taken by different objects, and your job is to find the distance and displacement of all three objects. Each square represents 1 meter. So here we have a little infographic, and this blue line is the path taken, so the object goes bloop, 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 and the distance is going to be following that entire path. Whereas the displacement, you just take the initial position and the final position, and you find the difference between them. So go ahead and pause the video for you to try out this one, and I will reveal what it is on the next slide. Okay, so the distance was 31 meters. You just count up all of the squares, and the displacement was 9 meters to the east, or you could just say 9 meters I hat. And I got that by counting the squares. So for this one, I'm going to give you a second to do it. Go ahead and pause and try. Okay, so the distance was 17 meters. If you just count the squares, that's what you get. And the displacement was 16.64 meters northeast, excuse me. So to do that, you're going to use the Pythagorean theorem, where this is a right triangle. So you're going to do a squared plus b squared equals c squared. And yeah, if you guys need help with any of the examples that are on this goes for every example. They're all numbered up here in the left corner. If you need help with any of those, then I have videos where I am solving all of them and I'm going through all the steps. So that might be helpful for you. Okay, try this one. Here we have the distance is 17.66 meters and the displacement is 1.41 meters northeast. Okay, whoa. I clicked a button, sorry. Velocity and acceleration. So here we have average velocity is the change in x over the change in t, and acceleration is also the change in v over the change in t. This is just a different way of writing delta. You would do f minus initial. Sometimes it's an I for initial, and sometimes it's a 0 or not. Just be aware of that. So the following slides describe the motion of different objects. Find the average velocity and acceleration for each scenario. The first one, example number 4, an object travels at a constant velocity 100 meters in 250 seconds. What is the velocity and what is the acceleration? Go ahead and pause. So the velocity is 0.4 meters per second, and the acceleration is 0 meters per second squared because it's a constant velocity, so the change in velocity is going to be 0. An object travels 100 meters in 250 seconds. Its initial velocity is 0, and its final velocity is 0.8 meters per second. What is the average velocity, and what is the acceleration? Average velocity is going to be the same at 0.4 meters per second, except for the acceleration is now 0.0032 meters per second squared. You could also write this as 3.2 times 10 to the negative third, up to you. Okay, example 6. An object travels at a velocity of 20 meters per second in the positive x direction for 10 seconds. How far does the object travel? So it's going to be 200 meters. You just need to do a little bit of algebra to figure this one out. So yeah. Now we have our kinematics. The kinematic equations is a set of equations that describe how an object moves when it has constant acceleration. So that is the key. We are only going to deal with constant acceleration in this course. So the kinematic equations will work for all of our problems in here, but do keep in mind that it is only for a constant acceleration. So I have our little key for our terms over on the right over here, and that's VF is final velocity, V naught is initial velocity, A is acceleration, T is time, and delta X is our displacement. Remember that velocity and acceleration are still going to be vectors, so they do technically have the arrows on them, but whenever I was putting it in the presentation, it looked super confusing and they were all overlapping and it was hard to read. So I just am not going to use the arrows on top, but please know that velocity and acceleration are vectors. Okay, so the first equation is final velocity equals initial velocity plus acceleration times time. The second one is final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Then we have the displacement equals initial velocity times time plus 1/2 times acceleration times time squared. And finally, we have displacement equals the velocity initial plus velocity final over 2 times t. And v naught plus vf over 2 is going to be our average velocity. Okay, so using the kinematic equations, sometimes you're only going to have a few pieces of information to work from. And to know all of the information about a system in motion that is experiencing constant acceleration, you have to use these equations. So the next few slides have example problems for you to work on, and I've worked out the first problem on the slide for you guys. And so I'll kind of walk you through how I like to approach this. So, example 7. A car starts from rest and then accelerates constantly to a velocity of 7 meters per second in the positive x direction in 10 seconds. What is the car's acceleration and what is the car's displacement? So I always start with writing down my knowns. And so I know that the initial velocity is 0 meters per second because it starts from rest. The final velocity is 7 meters per second, and our delta t, or the time, is 10 seconds. And then I'm going to go ahead and write the relevant equations that I need to use. So for this one, I have final velocity equals initial velocity plus acceleration times time. I knew to use this one because I have final velocity, I have initial velocity, I'm trying to find acceleration, and I have time. And then I'm also going to need delta x is equal to initial velocity times time plus 1/2 at squared. And I know to use this one because I'm trying to find displacement. I have initial velocity, I have time. This is 1/2 is a constant. I will know acceleration after this equation, and I have time. So I just go ahead and plug all of my values into the equations and do some algebra to get my answers, which is acceleration is 0.7 meters per second squared. Also notice that I keep my units in here. I know that I am doing this correctly. I'm on the right track because all of my units match up at the end. I have my meters per second. This goes to 0 over 10 seconds. Meters per second over second is meters per second squared, and that is the unit for acceleration, so I know that's correct. My delta x formula is here. I plug in all of my numbers, and that gives me the right units and 35 meters. Okay, so example 8. A car starts from rest, then accelerates constantly to a velocity of 20 meters per second in the positive x direction in 30 seconds. What is the car's acceleration and what is the car's displacement? Go ahead and pause and take a second to figure this one out. So the acceleration is going to be 0.667 meters per second squared, and our displacement is going to be 300 meters. Example 9. A car has a velocity of 30 meters per second in the positive x direction, then it accelerates constantly to a velocity of 20 meters per second in the positive x direction in 5 seconds. What is the car's acceleration and what is the car's displacement? So the acceleration is going to be negative meters per second squared. Since our acceleration is going in the opposite direction of our motion, or our velocity, I should say, it is going to be negative. And our displacement is going to be 125 meters. Okay, this is our last velocity acceleration example, and it is a car has a velocity of 30 meters per second in the positive x direction. The driver of a car sees a deer in the road 50 meters ahead. The maximum negative acceleration of the car is negative 10 meters per second squared. What is the maximum reaction time they have to stop the car? The time is going to be 0.167 seconds. This is a reminder from me to you. When you are driving, please be careful. Please do not speed. Please be alert. That is not a lot of reaction time. So just a warning, be careful. Okay, free fall and acceleration due to gravity. Free fall is a special case of one-dimensional motion where the only acceleration is due to gravity. And the acceleration due to gravity is represented by little g, and we have little g is equal to negative 9.8 meters per second squared. So this is an acceleration, and a cool fact is that everything in free fall is accelerating at the same rate. So in practice, in like the real world, there are things like drag and friction and air resistance, and all of these things are going to affect the way different items fall. But if you are in a vacuum, those things don't matter. And so there's this really cool experiment, and I encourage you to look up this video where people have in a vacuum chamber a bowling ball and a feather, and they drop them at the exact same time, and it's a really beautiful demonstration of the acceleration due to gravity, and they fall at the exact same rate. So we can use this acceleration due to gravity to find the rate of anything that is falling, regardless of its mass. So the first one I have for this is an object is dropped from a cliff 100 meters high. What is the object's velocity just before it hits the ground, and how long does it take for the object to hit the ground? Our velocity is going to be 44.267 meters per second, and our time is 4.5 seconds. Example 12. A person throws a ball straight up in the air with an initial velocity of 5 meters per second. How long does it take for the ball to reach its initial position, and how high does the ball reach? Okay, this one you would need to use kinematics for, and we have our time is t equals 1.02 seconds, and our height is going to be 1.276 meters. Okay, we've made it to graphing. So sometimes it's necessary to represent an object's motion with a graph. For this course, we are going to focus on three main types of motion graphs. So we have position versus time, velocity versus time, and acceleration versus time. For our position versus time graph, it shows position as a function of time. This means that time is the independent variable. It's on the x-axis, while position is the dependent variable. It's on the y-axis. So the object's position at t equals 15. Go ahead and pause the video, look at these questions, see what conclusions you come to, and you can look at the answers in my video. Okay, for a velocity versus time graph, we show velocity as a function of time. Again, time is our independent variable and velocity is the dependent variable. So go ahead and pause and figure out these answers to these questions, and we'll meet back in a second. Okay, acceleration versus time. An acceleration versus time is acceleration as a function of time. Time is the independent variable, and acceleration is the dependent variable. And go ahead and think about these questions for a second. Okay, so here's an example of some different graphs. For a stationary object, this means its velocity is 0. We have its position is not changing over time. It's just going to be a straight line. Our velocity, again, it's stationary, so it's equal to 0. It's going to be 0 for all of time. And our acceleration, since our velocity is 0, our change in velocity is 0, our acceleration is going to be 0 as well. Uniform motion means it's traveling at a constant velocity, so our position versus time is going to be a linear function. And our velocity is going to just be a straight line because it is constant. And then our acceleration is going to be 0 because our velocity is constant. Velocity final minus velocity initial is going to be 0. So acceleration is 0. And motion with a constant acceleration. We have a kind of exponential curve. And this is because as time goes on, the position is going to be changing faster and faster. And this is a positive acceleration. And for our velocity, since the acceleration is constant, it is going to be a linear function. And our acceleration is going to be just a straight line. It is constant, and so it's, a straight line. Okay, this is a distance versus time graphs showing some different scenarios, I guess I could say. So this is an object that starts at a steady speed, it stops for a minute, and then it returns to start. This is an object that is going quick because its slope is pretty steep, and it is going at a constant speed because it is linear. This curved function is an object that is getting faster. Here I have last one, a velocity versus time graph. We have this segment. The first segment is going to be a positive acceleration, so our velocity is changing. And this segment is a constant velocity, so there's 0 acceleration. And again, the velocity is changing, and this is going to be a negative acceleration. As you can see, it goes with the slope. So a positive slope is a positive acceleration, and negative slope is a negative acceleration. As you saw in example problems 13 and 14, we know that the derivative of our distance versus time graph, the slope of our distance versus time function is going to be our velocity, and the slope of our velocity versus time graph is going to give us our acceleration. So go ahead and practice on doing some of these problems and work on your practice problem sheet. If you get stuck on any of these problems, go ahead and watch my video that I have of myself doing these problems for you guys. And I will check back in a couple days. Thanks.